Section 4.5, linear approximations and differentials. All right, let's dig into this topic of linear approximations. Assume that f is differentiable and we're looking at its derivative at some point a. So we're interested in f prime of a. Limit definition is shown. We want to think about what happens when you have an x value that's close to a. What's going on with the graph situation? So if we look over here to the right, they're showing us a function with the tangent line drawn at some point a, f of a, and then they zoom in and they zoom in again. And when they zoom in a couple times, notice that in this section, like from here to here, it's hard to tell the difference between the original function and its tangent line. So that's the first answer that we want to give. So what happens when x is close to a? The original curve and the tangent line look the same. And so then what we want to say from there is if you can't really tell the difference between the original function and the tangent line, then if you needed to plug into the original function and the x was close to this point of tangency, would it make much of a difference if you just plugged into the tangent line instead? And the answer is probably not. So let's think about what the equation of the tangent line would be. Let's suppose this is our point right here and that it's at a, and therefore its y-coordinate would be f evaluated at a. And then the slope of the tangent line would be the derivative at that point. So what would be the equation of the tangent line? Well, we normally go y minus y0 equals m times x minus x0. So in this case, that becomes y minus f of a, because f of a is our y-coordinate at our point of tangency, equals the slope, which is f prime of a times x minus a. And then what we do is we add the f of a to both sides, and we get y is equal to f prime of a times x minus a plus f of a. So that's the equation of the tangent line, and we want to use that for this idea of a linear approximation. Suppose f is differentiable on an interval I containing the point a. The linear approximation to f at a is the linear function L of x equals, and then what we're going to use for the L of x equals part is just the other side of this. So we're replacing y by L of x to write it as like linear function, and we know it's the equation of a line because it's just the tangent line formula. But our linear approximation x becomes f prime of a times x minus a plus f of a. And we're going to use this linear approximation to approximate values of the original function near the point of tangency. Sounds pretty complicated, I suppose. Let's try and make more sense out of it by looking at this example down here. So find the linear approximation of f of x equals the square root of x at x equals 9. All right, so that's a new way of saying something old. Really, all they're asking us to do is find the equation of the tangent line at x equals 9. So we just do our normal procedure for that. So f of x is x to the 1/2. So that means that f prime of x would be 1/2 x to the negative 1/2, or f prime of x would be equal to 1 over 2 times the square root of x. All right, so what would the slope of our tangent line be? The slope would be f prime at a, and the a they're interested in, this specific point, is 9. So we do f prime of 9. That'd be 1 over 2 times the square root of 9, or 1 over 2 times 3, so 1 over 6. That's the slope of our tangent line at x equals 9. How about the y value? Plug that 9 into the original function, and you just get the square root of 9, which is 3. So if we just found the regular equation of our tangent line, we would do y minus the y-coordinate, which is 3, equals the slope, which comes from the derivative and is 1/6, times x minus 9. And if we add 3 to both sides, that gets y by itself. That also puts it in the format above. So I'll replace y by L of x. So the linear approximation x is 1/6 times x minus 9 plus 3. So all I really did there is find the equation of the tangent line, but we're now referring to that as a linear approximation. And when we turn the page, we'll see why. All right, continuing on with the example from the previous page, I've copied over our linear approximation right here. And now I want you to have a look at the two together, the original function and its linear approximation. So the red graph is y equals the square root of x, and the blue graph is this linear approximation, or the tangent line at 9. And so the key thing I want us to see is, like in this section right here, it's really hard to tell the difference between the two. So if they asked us to approximate the square root of 9.1, and instead of putting that into our calculator, or instead of plugging it into the original function, we just plugged it into the linear approximation, we should still get a pretty good answer. So that's what we're going to try and do here. We're going to say the square root of 9.1 can be approximated by looking at the linear approximation formula at 9.1, which would be 1/6 times 9.1 minus 9 plus 3. So 9.1 minus 9 is just 0.1, and then that's divided by 6 and plus 3. And if you just put that into the calculator and came up with a decimal for that, it's approximately 3.01667. Now, if you were to take the square root of 9.1 and just evaluate it directly on a calculator, put in the square root of 9.1, you get approximately 3.01662. So notice that the first 5 digits of those are the same, and it's that 6th digit is where we first see a difference. So it's a really close approximation if we plug into the tangent line instead of plugging into the actual square root function. Sometimes I refer to this as like broken calculator math. Like if you ask somebody to calculate the square root of 9.1, they're just going to plug it into a calculator. And if they don't have one, they're probably going to be kind of stuck as to what they can do, because people don't do square roots of messy numbers in their head. But we can, with pencil and paper, do multiplication, addition, subtraction, division. And if you look at the stuff that goes into the linear approximation method of getting the answer that was really good, only off in the last place, what kind of math are we doing? Division, which we can do, subtraction, which we can do, addition, which we can do. So all the math that went into this linear approximation is something that we could do with pencil and paper, whereas the square root of 9.1 the right way, by plugging into the square root function, is something we depend on a calculator for. But here's a way we could get a pretty decent answer without one. All right, let's try the same thing to approximate the square root of 3.9. So we'll just do the exact same technique. Sorry, let me just get the color back to blue. So we're going to try and get the square root of 3.9 by approximating it by plugging into our linear approximation that 3.9. So it'd still be 1/6, but now it would be 3.9 minus 9 plus 3. So let's see, 3.9 minus 9, I believe, is negative 5.1 over 6 plus 3. And if you work that out, it actually comes out pretty nice. And again, it's just division and addition, so we could manage it with pencil and paper. Turns out to be exactly 2.15. But if you were to put the square root of 3.9 into a calculator, what would you get? Well, first of all, the square root of 4 is 2, so the square root of 3.9 is smaller than 2. And notice the answer we got is bigger than 2. So can already tell this isn't going to be a great answer. If you put it into the calculator, the square root of 3.9 is 1.97484. So none of the digits match up with what we got from the linear approximation. So then the question is, why was square root of 9.1 so good, and why was the square root of 3.9 so bad? And the answer comes from the graph. We found this linear approximation by doing a tangent line at 9. And in that zone, they're very close. But then we tried to get an approximation for 3.9, which is over here, and in that spot, the tangent line and the graph are no longer close together because we're not near the point of tangency. So why is there so much error? Because 3.9 is farther from the point of tangency. And when I say it's farther from the point of tangency, I mean farther than the 9.1 was. So what's the fix to that? If we wanted to get a good square root of 3.9, we could do it, and we could still do it by using linear approximation, but just don't do it where x equals 9. Instead, pick a number that's close to 3.9 that we know the square root of in our head. So the closest number to 3.9 that we know the square root of is 4. So if we redo our linear approximation at 4, then we can attempt to use that to get the square root of 3.9, and it should be much better. So we already know that f prime of x is equal to 1 over 2 root x. We did that on the previous page. So now that means that f prime of 4 would be 1 over 2 times the square root of 4, which is 1 over 2 times 2, or 1/4. And then we need f of 4, which is the square root of 4, which is 2. And then we can get our tangent line by doing y minus the y-coordinate, which is 2, equals the slope of 1/4 times x minus the x-coordinate, which was 4. And then we add 2 to both sides, and we change from writing y to writing L of x for the linear approximation. And so L of x is equal to 1/4 times x minus 4, and then that minus 2 gets moved over, and now it's a plus 2. And then when we want to know what is an approximation for the square root of 3.9, we can approximate that by plugging 3.9 into this new linear approximation function, where the point of tangency is very close to 3.9, and therefore the tangent line and the graph should have very similar values. So let's see if it works. We get 1/4 times 3.9 minus 4. minus 4, and then plus 2. And then 3.9 minus 4 is negative 0.1 divided by 4 plus 2. When we do that, we get 1.975 exactly. And then let's compare that to the actual square root of 3.9, which we wrote down up above. We had 1.974, but followed by an 8. So if you rounded that to 3 decimals, it would be 1.975. So now we're getting a very good approximation, whereas before we were getting a bad one. And what was the difference? The difference was how close the number we were trying to plug in was to the point of tangency. So does linear approximation work well to approximate values of a function using its tangent line? Yes, but only if the number you're plugging in is very close to the point of tangency. And the further you get away from that point of tangency, the less reliable that linear approximation is, and the more that we would tend for it to break down and have big error as the gap grows between the function and the tangent line. All right, moving on to another example, we're going to try and estimate the sine of 3 degrees using a linear approximation. So when you use this method, you want to find the equation of a tangent line to the function and somewhere near the point that you want to plug in. So we want to plug 3 degrees into sine. So we want to find the equation of a tangent line to the sine function at an angle that's nice and near 3 degrees. When we say an angle that's nice, we mean that one we know in our head, probably. So what do we know and have memorized? Sine of 0 degrees, 30 degrees, 60 degrees, 45 degrees, 90 degrees. So the one that's closest to 3 degrees from that list is the 0 degrees. So what we're going to do is try and find the equation to the tangent line of f of x equals sine of x at 0 degrees, a nice point near 3 degrees. So we find the derivative first. F prime of x would be the derivative of sine, which is cosine. And just a quick point on that, the derivative of sine is only cosine if we're in radian measure. So when we do our work, we're going to have to do everything in radian measure, so we're going to have to eventually convert that 3 degrees. But what we're doing is trying to find over here on the right the equation of this tangent line that they've shown, which would be this blue line that I just shaded in yellow. At 0, 0, they're the same. And that red dot they're showing, so that red dot right, let's make it pink, I guess, like right there, that dot that they're showing. Notice that's just a tiny bit to the right. That's probably 3 degrees converted to radian measure. And if you look at the graph of the sine function, which is wavy, and the tangent line, which is straight, they seem to be very close together in that neighborhood. So if we plug into the tangent line, we should get a pretty good answer for our approximation of sine of 3 degrees. But we need a couple things first. To get the equation of the tangent line, we need to know the y value. So that's at the point of tangency. So we need to know f of 0, which would be sine of 0, which is 0. We would also need to know the slope, which would be f prime at 0, which is cosine of 0, which is 1. And again, that would be our slope. So that's equal to m. So our tangent line would be y minus the y coordinate, there's our y coordinate, equals the slope, which we have as 1, times x minus the x coordinate, which was 0. So we get kind of an interesting tangent line here, just y equals x. And if you look at the line they drew, that seems to actually be the line y equals x going through the origin. So our linear approximation function, L of x, is just equal to x itself. So this is going to be a pretty easy one to plug into, but first we need to get the right number to plug in, which isn't 3 degrees, but 3 degrees in radians. So take the 3 degrees, put it over 1, and then multiply that times pi over 180 degrees. Pi is half a circle rotation, so is 180 degrees. So those are the same angle in different formats. So when I multiply by that conversion factor, the degrees cancel and 3 goes into 180 60 times, and we get that 3 degrees is equal to pi over 60. So what is the linear, let me back up here a little bit. What is the sine of 3 degrees? Well, first of all, that's the same thing as asking for the sine of pi over 60. But we need to do it in radian measures, so we'll use that pi over 60 to plug into our linear approximation function. So that's going to be L of pi over 60. And we should note at that point, that's where we're starting to approximate, because instead of plugging into actual sine, we're going to plug into the equation of the line instead. But this function is very simple. It says whatever you put in is what you get out. So if we plug in pi over 60, we're going to get out pi over 60. So the approximation here is that the sine of 3 degrees is equal to pi over 60. Now if we plug pi over 60 in on our calculator just to see what that is as a decimal, it's 0.05236. And if we were to plug sine of 3 degrees into our calculator to see what the exact answer is, we would get that sine of 3 degrees is equal to 0.05234. So it becomes different in the 6th decimal place, but until then the two matched up. So can't tell much of a difference between the tangent line to sine and the sine curve itself at that 3 degree spot, so we get a very similar answer when we plug 3 degrees into the equation of the tangent line versus if we plugged it into the real thing. We have some values of a sine memorized, like sine of 30 degrees is 1/2, sine of 60 degrees is root 3 over 2. We don't have sine of 3 degrees memorized, but a lot of people do know several decimal places for pi, and we can do long division by 60. It's messy, but we could do it with a piece of paper. So this is showing a method that could give us some reasonable approximation for trig values, even if we didn't have a calculator. So again, this is why I kind of refer to these as broken calculator problems. All right, so apparently one use of linear approximation is if you ever get shipwrecked on an island and you don't have your calculator with you, and if only you knew the sine of 3 degrees, accurate to like 4 decimal places, you could escape. You could use this idea of linear approximation without your calculator, just sketch it out in the sand and do some division, and you'll get the approximation you need. All right, hopefully we can find some other uses besides broken calculator uses, and here comes one. So another form of linear approximation says, take this formula and take the f of a and move it back to the left by subtracting it from both sides. And then think about what you have on the left. Since that's f of x minus f of a, that's a change in y values, and that's approximately equal to f prime of a times, and instead of x minus a, we'll write that as the change in x values. So if you're trying to approximate how much the output of a function is going to change, you can get that approximation by taking the derivative at a nice starting point times the change in the x that's occurring. So let's see an application of that. Approximate the change in surface area of a spherical balloon when the radius decreases from 5 inches to 4.9 inches. And note surface area for a sphere is a equals 4 times pi r squared. All right, so what we want to do is take that part up there in blue and translate it into this problem. So the change in y is the output variable, so that would become change in a. And instead of writing f prime, I'll write a prime. So delta a would be approximately equal to a prime evaluated at some nice starting point, and our radius started at 5, so that's going to be our a. So we would do a prime of 5, and then times the delta of the input variable, which in this case would be the radius. So if we want to approximate the change in surface area, we can find the derivative of the area function, evaluate it for the radius of 5, and multiply it by how much the radius is changing, and that should give us a decent approximation. So let's go off to the side over here and do some work. A prime would be, bring the 2 down, and we would get 8 times pi times r to the first. Reminder, pi is not a variable, it's a constant, so that 4 pi is just out front getting multiplied by the 2. All right, so then what would a prime of 5 be equal to? Well, if we plug the 5 in there, we get 8 times pi times 5. So we end up with 40 pi. And then how about the delta r? So delta r would be x minus a. So if 5 is the a, then the x that we're moving to that's nearby is the 4.9. So we would do x minus a would be 4.9 minus 5, which is negative 0.1. So the change in surface area is approximately a prime of 5, which is 40 times pi, times the change in r, which is negative 0.1. So the negative moves out front, that decimal changes the decimal on the 40, and we get negative 4 pi. Okay, and then what would the units be? Since this is area and the radius was given in inches, it would be negative 4 pi inches squared. Notice, by the way, that the negative does make sense, because if you're letting air out of the balloon and the radius is shrinking, the balloon's getting smaller, so its surface area would be decreasing. So there we are using this idea of linear approximation to estimate the change in surface area on a balloon where all we know is how much its radius shrank. It's not the exact change in surface area, but it should be a good approximation because we're just moving a small bit away from our point of tangency. All right, let's explore this a little bit more through the topic of differentials. Consider dy dx equal f prime of x, or the slope of the tangent line. The dy and the dx represent change in the tangent line. So when we think of f prime of x as slope, we would think that slope is usually change in y over change in x. When we're writing that in the calculus setting, we express the change in y as dy and the change in x as dx if it's for the tangent line. But if the change is for the actual function, we represent it as delta y and delta x. So that can be a pretty confusing idea. So we have a picture here to kind of show the idea. We have this curved function y equals f of x. We found a tangent line at this point of tangency right there. And then we're looking at, well, what if you moved over a little bit to the right? How would you express that? So let me do some tracing out here. If you were talking about the function itself, and you looked at going over this far, and then you went back up to the curve again, so over here and then up to there, that vertical change would be a delta y because it's on the actual function, and the horizontal change would be a delta x because it's for the actual function. Now, if you were to do that on the tangent line, then the change in x is still going to be the same. We would call it delta x now because it's a change for the tangent line, but it's still the same over distance. But when you go up, you wouldn't go up as far because you would just go up until you hit the tangent line, and that smaller up right there, in this case smaller, is the dy. So whether you're going, when you move over to the right some amount, whether you called that dx or delta x, it would represent the same quantity. But when you talk about the change in the vertical, the dy is the change that would occur on the tangent line, and the delta y is the change in height that would occur in the function, and those are not always the same. But if the change is small, they're almost the same. So what we want to do take advantage of with this differentials idea is if you just look at a small change in x, then delta y and dy and delta y are almost the same. And dx and delta x are always the same. dy and dx are called differentials. And so when they say use differentials to make some approximation, this is what they're talking about. And so what's the idea here? If you want to know the change in the actual function, you could approximate that by finding the change in the tangent line. So let's look at that in an example to try and make better sense out of it. Use the differential notation to approximate change in f of x equals 1 over x cubed, assuming a small change in x. All right, I'm going to change that over to y notation just because that'll match what's up above and be easier for us to translate. So let's rewrite this first of all as y equals 1 over x cubed. All right, so let's find the derivative. The derivative would be, well, first of all, let's simplify it. If y equals x to the cube, 1 over x cubed, then y equals x to the negative 3. Now let's find the derivative. So dy dx, which we could call y prime, but we want to use this differential notation to make this work. Dy dx would be equal to negative 3 x to the negative 4. And then that implies dy equals, and now all we're basically doing here is multiplying both sides of this by dx. So a dx here and a dx here. These would cancel, and you'd get dy equals negative 3 x to the negative 4 dx. All right. So that's what dy is equal to, but they wanted us to use differential notation to approximate the change in f. So we can write down the change in f that they want from us, but I've substituted y in place of that, so that would be equal to the change in y. And according to the differential idea, change in y can be approximated by dy, which in this case is equal to negative 3x to the negative 4 dx. So to answer their question directly, approximate the change in f of x, we could say that the change in f of x is approximately equal to negative 3x to the negative 4 times the change in x, or dx, using the differential notation. So now use that to approximate the change in y as x changes from 1 to 1.5. So they're using the change in y idea now, but change in y, change in f are the same. So we're still going to find that by using this right here. So change in y is equal to change in f. So therefore it's equal to negative 3 times the x that we're starting at, which is 1, times the change in x, sorry, that's still to the negative 4th, and then times the change in x. And if you go from 1 to 1.05, how much of a change in x is that? We're adding 0.05 from 1 to get 0.05. So the change in x is 0.05. 1 to the negative 4 is still 1, so we just get negative 3 times 0.05, so we get negative 0.15. So differentials can help us to approximate the change in the output variable by taking the derivative times the change in the times the change in the input variable, where we plug the nice starting point into our derivative and we plug the difference or change in the input variable in place of the dx portion. All right, that wraps up section 4.5.